So good afternoon and welcome everyone. Hello. This is the Decarbonisation Technical Workshop at Energy Innovation 2021. My name is Connie. I'm from the Institute of Chemical Engineering and Sciences at ASTAR, and it's my pleasure to be your moderator this afternoon. In order to realise Singapore's Green Plan and to meet the ambitious targets that have been set to combat climate change and to transit into a low carbon future to achieve long-term net zero emissions, we require a concerted approach amongst our research performers from IHLs and ASTAR, technology experts, government agencies, and industry in order to encourage translation adoption of decarbonisation technologies. In a forum like today's, we aim to promote the dialogue, knowledge sharing, and networking opportunities to facilitate achieving this national vision. In this segment, for the next hour, we will hear from 3 eminent speakers who are working in the field of decarbonisation, representing perspectives from IHL, government agencies, and industry. Each of them will be sharing on technologies, capabilities, and initiatives in decarbonisation, and this will be followed by a panel discussion at the end of the presentations. We will be taking the Q&A at the end after all 3 presentations, but feel free to start posting questions in the chat box. So without taking up further time, I will now invite our first speaker today, Associate Professor Chen Leeway from the Institute of Chemical Engineering Sciences at ASTAR to give her presentation. She is a team leader in the Process and Catalysis Research Division and is active in both academic and industry-related R&D. Her publications have been highlighted in prestigious catalysis journals, and she has led the development of a methylation catalyst with IHI, which has been successfully demonstrated and licensed in 2020. This afternoon, she will be presenting on the CCUS capabilities and initiatives at ICIS. Leeway, please.
Okay, I will share my screen. So can you see my screen now? Hi, hello. Are you able to see my screen?
Yes.
Okay. So good afternoon, everyone. Thank you for being here today. So let me start my talk on the CCUS capability and initiative at ICES. So this is the outline of my talk, and 3 key research areas will be highlighted. As we all know, carbon dioxide is a climate killer. However, it should be considered as a valuable raw materials. In fact, carbon dioxide can be used to make many useful products such as building materials, chemicals, and fuels. And it's predicted this will be a $1 trillion market. So carbon dioxide should be reused instead of pulling carbon again from fossil resources. And CCU technology is a key to helping us meet our climate goal as well as economy goal. And in the past few years, ICES has been working on the development of CCUS technology across the value chain. We work on capture, storage, and utilization. And in the meantime, we also have other capabilities such as process design and safety, techno-economy analysis, and life cycle assessment to support the research. And last but not least, importantly, recently we initiate the conceptual design of a carbon capture and utilization translation testbed. So let's go to our first topic on CO2 mineralization. And we know human beings are facing the threat of sea level rising. And Singapore is very vulnerable to this because our 30% land in Singapore is lower than 5 meters above the sea level, including many important areas such as Jurong Island. So we need a large amount of sands for the coastal protection. And actually, CO2 mineralization is able to utilize waste carbon dioxide to do the mineralization. And this will generate a solid carbonated material and is useful for then degradation. And the raw material can be used is not limited to the natural minerals. Other waste materials such as incineration bottom ash, waste from construction, all can be used for these mineralizations. And ICES has developed a novel CO2 mineralization technology. So in the next slide, let me take you through a little bit in the technical details. Let me show my laser pointer. Yeah, okay. So we start with aqueous ammonia as a CO2 absorption sources. And in this absorber, carbon dioxide from flue gases with different concentration is able to react in the aqueous ammonia in this absorber. And ammonium bicarbonate will be generated from this reaction. And the solution will be sent to another reaction chamber. And this reaction chamber, we will feed in raw materials such as natural mineral, RCA, and IBA. And the carbonation reaction will happen in this reactor. And after the reaction, the ammonia can be regenerated and back to recycle. And we will obtain the solid carbonated materials from this reaction. And this carbonated material can be used for different purposes, such as alternative stands. And in case if this mineralization is not required, and this ammonium bicarbonate can send to another desorption column. And from here, pure carbon dioxide can be dissolved from ammonium bicarbonate, and pure carbon dioxide can be used for downstream applications. And the ammonia can be recovered and sent back to the system for next step of reaction. So the novelty of our process is that it's a very flexible in capturing different CO2 concentration, including the very diluted carbon dioxide from flue gas. This is a very typical gas from Singapore's power generation plant. And our process is relatively low energy cost because it can be just operated at room temperature and ambient pressure. And the process avoids the use of some environmental unfriendly binders and additives. So our technology actually can bring 3 benefits to Singapore. It can reduce carbon dioxide emission, permanently fix carbon dioxide in solid materials. And these materials, if we use some of the waste material, and it will reduce the landfills. And in the meantime, this can be used as alternative sands or as building materials. And in the meantime, that means we can reduce sand imports. And our technology has attracted interest from many public agencies and industries. So we are aiming to scaling up the technology and for the field testing in future. And we're also looking for collaboration opportunities to bring up this technology to commercial scale. Okay, so we go to the next topic, CO2 to fuels and chemicals. And the first topic is CO2 methylation, use renewable hydrogen. And as you can see from this graph, and if we making methane from CO2 and renewable hydrogen, and we call this methane as substitute natural gas. And from here you can see as an energy carrier, this SNG has much higher storage capacity and the longer time of storage compared to many other different types of energy carriers. And here shows the example of Audi power to gas e-gas project. So they can use this substitute and SNG as energy carrier to convert renewable energy into methane. And this can be used to drive cars So with IHI is a Japanese heavy industry company, and we have been working with them for years to develop catalysts and technology for this CO2 methylation. And we have developed a very unique structural catalyst, which is flexible, can be synthesis for a wide range of nickel loading as the active phase for the reaction. And this catalyst is very robust. It has good coking resistant and sulfur resistant, sintering resistant as well. So you can see here we have much smaller particles after reaction compared to a benchmark, commercial benchmark catalyst. And this catalyst has been tested in Japan as well, the field test, as well as in the lab test for CO2 and as well as CO methanation reaction. And the catalyst has been shown very good thermal stability and also activity compared to a benchmark commercial catalyst. So together with IHI, we have successfully to translate this catalyst and technology from very small lab scale up to now is 0.5 tons per day CO2 commercial industrial scales demonstration at Japan Soma Green Energy Center. And the next topic is the CO2 to jet fuels. And you can see here in Singapore, 2017 alone, we consume about 8 million tons of jet fuel. And this will release millions of tons of carbon dioxide. And although there's solutions by using battery or hydrogen to decarbonize this aviation industry. However, there's a limitation because compared to hydrocarbon fuels, these hydrogen and battery, actually they have very, very low energy intensity compared to the hydrocarbon fuels. And they're not drop-in fuels, which means you need to have a lot of change on the infrastructure overall. However, biofuel is another choice, but the availability of biofuel is also very limited. So CO2 can be used as raw material to make jet fuel actually. And this is a significant advantage because we can help to reduce CO2 emission and also help to the decarbonization of aviation industry. And in ICES, we are working on this direct thermocatalytic conversion of CO2 to jet fuels. And compared to the current two-step approach, we are using a one-step direct approach. And this approach has advantage such as smaller footprint, simpler process, and higher energy efficiencies. And all this will have cost reduction. And with the support of UGT A-star seed funding, we have some very promising preliminary result. So this is the red color is our catalyst, and we benchmark it with some good literature results, and results are quite comparable. And of course, compared to the thermodynamic limitation prediction, we still have rooms to improve the catalytic performance. And the next one is CO2 to methanol. So this is a work from an A-star scholar, Mr. Mohammed, and he has been co-supervised by NUS Prof. Zeng and A-star ICES Dr. Armando. And the beauty of this work is if we, through this architecture design of catalyst support, and we generate these hierarchical porous structures, it greatly improves the diffusion during the reaction and also have the small confined space for the nano copper particles. So with this kind of structure, this catalyst is be able to achieve much higher copper yield and the selectivity to methanol compared to a commercial syngas-based methanol catalyst. And it has shown higher stability, and also we can gradually reduce the loading of active metals. So this page summarizes our catalytic conversion of CO2 to fuels and chemicals. So we can work on catalyst design, scaling up, reactor process design, and also system integrations. So with the support of our accelerated catalyst developed platform with our sister RI, Emory, and IHPC, and this translational testbed, we hope we can accelerate the transformation of the technology from that to commercial pilot plant testing scales. And so the next topic is this transportation testbed. So why do we need this testbed? And it's well recognized that there's a value of that in the translation of research ideas and into industrial scales, particularly in the process industry, where the scale and the cost of failure, they increase with the TRL level. That's why companies are very selective when they choose the technology to test bed. While research performance, they always have limited resources to validate their breakthrough ideas at larger scales. So this is really many breakthrough ideas fall into this valley of death. And this is where the major de-risking is necessary. And in addition, a single technology, usually it will take about 10 years to be commercially available in the chemical industry. So the question for ICES is whether we can move away from this conventional approach to be faster and more cost-effective and more flexible in developing not just a single technology, but with multiple different emerging technologies and help companies to de-risk business decisions. So our response to this is a unit, first in its kind, flexible, modular, plug and play testbed, which will allow us to rapidly adapt a testbed to perform and demonstrate of different types of emerging CCU technology. It can be from research performers, startups, or technology providers, and under the more realistic industrial conditions. So the examples of the CCUS technology can be like membrane for CO2 capture, liquid and solid-based capture technology, or CO2 conversions. So we hope through this concept, we can achieve the acceleration of the translation of CCU technologies and de-risk business decision for the next step of industrial piloting or ultimately adoption. So this comes to the end of my presentation with 3 key takeaways. ICES is active in research areas of CCUS with different TRLs. And the unique, first in its class, flexible, modular, plug-and-play testbed is at the conceptual design phase. So we hope this will greatly help the acceleration of the translation of technology. And we are looking for researchers and industrial partners for collaborations. And thank you for your kind attention.
Thank you, Leeway, for giving us an overview of the CCUS initiatives at ICES. Okay, so our next speaker is Prof. Chen Hua from NTU. Prof. Chen leads the hydrogen and fuel cell research at NTU and is currently the co-director of the Energy Research Institute at NTU. and is the Senior Vice President of China-Singapore International Joint Research Institute in Guangzhou Knowledge City, China. He has spun out a fuel cell company manufacturing key components for PEMFC, and also serves as a technology and technical advisor to Syndrogen Energy. During his career, Prof. Chen has received many awards and accolades and has published 271 refereed journal papers with more than 14,000 citations with a H index of 60. This afternoon, it is my great pleasure to welcome Prof. Chen, who will be taking us through hydrogen and fuel cell research that is conducted at NTU. Prof. Chen, please.
Thank you. Thanks for inviting me to share with you our work at NTU on our hydrogen and fuel cell research. You can see the picture here. We are throwing a die. I'm not sure, are we gambling, to decarbonize and using hydrogen to replace it? I hope not. All right. I hope that we are doing the right thing. This is today's what I'm going to share with you. Give a history, for the benefit of some of the audience, hydrogen and fuel cell research, development, and demonstration activities in Singapore. And secondly is my research, in the last 30 years, and some commercialization effort, and some of the proposed project aligned with the national decarbonization effort. So this is a busy slides, and if you look at those with a start of the effort that done in NTU, we set up a fuel cell strategic research program in 2001, and we organized the first World Hydrogen Technologies Convention back in 2005. And the subsequent year, A-Star formed the SERC fuel cell program, and I was joint A-Star under joint appointment arrangement as a program directors. And you can see that in 2014, NTU and EU's institution, major EU institution, form a consortium and work on solid oxide cell and the stack testing, safety and quality assurance. This will lead to the code and a standard for the application. The project was actually led by German Aerospace Centers and with a CEA and all the major institute in Europe. Right, and in 2018, we organized Hypothesis, which is stand for hydrogen power, the first EU's symposium that brought to Singapore. And in 2019, NTU and CSIRO hosted the Hydrogen Hub Development Workshop, and also we have currently 2 ongoing projects working together. And here you can see that some of the major investments. In 2003, Rolls-Royce came to Singapore, and in 2005, a consortium called Enertech was formed and sinking $100 million in the investment, right? And then in 2014, GIC invests 63 million in Intelligent Energy. These 2 are actually a British company, right? And then lately in 2018, there is a study on a hydrogen import and downstream application for Singapore and commissioned by NCCS, right? So these are the brief history that you can see. There are a lot of demonstration activities this year. Started from 2001, about 20 years of history. Next is the research that the hydrogens and fuel cells journey that I walked through. I started off with the methanol reformings, and then after that, with the support, funding support from British Gas, I'm working on the natural gas reformings. Then I moved to a solid oxide fuel cell, then after that PEM fuel cell, then electrolyzer cell, solid oxide electrolyzer cell, then PEM electrolyzer cell. More recently, my research effort more focused on the commercialization of a PEM technology, and then some of the cracking technology, including ammonia cracking, and CDM stand for catalytic decompositions of methane, or we call it methane cracking. Last but not least, some of the feasibility study. And the latest paper that we have published is on long-distance renewable hydrogen transmission via cable and pipeline. So this is actually, a case for Singapore that if we transport the hydrogen from Australia to Singapore, cover the distance of 4,500 kilometers, and look at the cost, look at a lot of the, constraint as well. So a snapshot of the hydrogen and fuel cell research over the last 30 years, you can see that there are many projects, including an industrial project that we make, a fuel cell system that we push to a Jurong Island and tap the gas from a chlor-alkali plant, actually is, this chemical industrial Far East, and proves that, the hydrogens from the industry can be used to generate the powers. And you can see that, these are fuel cell system developed in how a 5 kilowatts combined heat and the power system. We also fly UAV using the fuel cell, and some of the hydrogen generation projects as well. There are 4 laboratories, 3 of them. One is for the fuel cell fabrication and demonstration, including the methane cracking project. One is on the power to gas. Just now, Leeway also has shared that, something that converting the CO2 and the hydrogen into the methane. And we have one laboratory devoted to catalyst fabrication. And this technology has been transferred to industry. And the last laboratory I have is in China-Singapore International Joint Research Institute at Guangzhou Knowledge City. And this is to meant for the commercialization and support the industry on some of the fuel cell projects. And here you can see that the companies, that I set up in is commercialized through China-Singapore International Joint Research Institute. And the company focus on the catalyst mass production and CCM or MEA's mass production as well. And this has made into a fuel cell stack by our sister company and demonstrated in a fuel cell vehicle. And essentially, this is a range extender. It's not a full fuel cell vehicle. There are 2 7.5 kilowatt, make it 15 kilowatt that use methanol as a fuel, and onboard reform generate the hydrogen and for the vehicle. And the DPM Hing and the Governor Mark had actually visited the companies. Another effort is that NTU and Syndrogen Energy, form a partnership. I think if you read the newspaper in the last few days, Syndrogens actually was formed in March, and a JV companies of nanofilm in Temasek, and they set aside 140 million for this effort. And the core activities is manufacturers of the fuel cell. And the collaboration with NTU is on the PEM technology, and we license the technology to them to fabricate the CCM and the catalyst, key component design and manufacturing, and the full characterization of the fuel cell. Now come to the 4 projects that I like to share with you. That the first one is the methane cracking for turquoise hydrogen generation. Right. Essentially, this is a technology can potentially produce the hydrogen at a cost like SMR, but without the CO2. So methane is cracked into hydrogen and the carbon, right? The byproducts is the carbon is actually the graphite powder and can be valorized to offset the cost of the hydrogen. Traditionally, such a method is used to produce the carbon black. Carbon black has a lower values than the graphite, but even those people can afford to throw away the hydrogen because the carbon black is more valuable than the hydrogen. So hydrogen is used in that, the carbon black is used mostly in the tire of a car. So in this project, we produce the graphite powder instead of a carbon black, right? And this carbon black has a lot of graphite powder has a lot of application. One of the application you can think of is that can use in the batteries as a battery materials. if you look at the Tesla battery, one battery will need 96 kilograms of graphite powders. So, you are expecting that, there's a growth in the demand of the graphite when all the car on the roads are converted to the electric vehicle powered by batteries. So compared to other reactors, rotary kiln reactors can potentially be scaled up for mass production. So there are different kind of reactors, including fixed bed, free die beds, and then plasma reactors, or the use of the molten salt or molten metal. And we found that our studies show that rotary kiln reactors can actually scale up for the mass production. But the challenging part is for the research, including the catalyst fouling, the catalyst regeneration, and the continuous application, knowing that the carbon form, then there will be a separation of the carbon powders from the catalyst, and we need a two parallel system when one is on regeneration and the other one can be operate, so as to ensure the continuous operation of the reactors. There are different types of catalysts. Commercially, like the one that used by Hazel Group is iron. Irons has a relatively poor catalytic activities. The best one so far is still the nickel. The operating temperature is actually not as high as steam methane reformings. You can see that the temperature range here can be quite low, 500 to 650 using the nickel. And another one is seawater electrolysis. And solid oxide cell is perhaps the only technology that can operate in fuel cell and electrolyzer mode. So meaning that one device serves two purposes. This leads to the so-called less investment if such technology is to be used as an energy storage device. So the electricities to our hydrogen heating values can be more than 100% if a waste heat is available. So if you look at a concept, what is actually our electricity input, preferably is from the renewable energy. If we have a waste heat, right? So the waste heat and the electricity combined together based on the conservation of energy, the enthalpy of the hydrogen will have highest values than energy values than the electricity we put it in, right? So SOCTEC, which is the project I mentioned just now, is a European project, led by a German Aerospace Center. This is a completed project. Testing conducted under the reversible SOFC and SOEC mode, and following a wind profile recorded in a Danish island. So we run for 16 days, 3 hours solid oxide fuel cell mode, generate the electricity, and 20 hours solid oxide electrolyzer cell, generating the hydrogen. So we can see that this is a wind profile. The blue color is actually the excess energy that can be used to convert the electricity into the hydrogen and store it. And the pink colors are the moment that energy is insufficient. So you can use the hydrogen and reconvert it back using the solid oxide fuel cell and to generate the electricity. So theoretically, the efficiency is very high. The higher the temperature, the lower the energy input, the higher the enthalpy or the heating values of the hydrogen will be. This is a project that CO2 captures from an oxy combustion power plant. So essentially, in an oxy combustion plant, oxygen is used as an oxidant instead of air. So the exhaust gas are nothing more than the waters and the CO2 without the nitrogen. So making the CO2 concentration very high. In addition to the exhaust gas, we have the waste heat. And if we co-electrolyze the waters and the CO2 using the renewable energy, this would mean that we are bridging the fossil to the renewable energy application, right? This is a fossil, this is a renewable. So in a single step, we produce the syngas, hydrogen and the CO, and the byproduct is the oxygen, and oxygen can feed back to the power plant. we know that 1 mole, if we burn the methane gas, 1 mole of the methane is fully oxidized into CO2 and water. We need 2 moles of the oxygen. And this, the byproducts is actually 1.5 mole, 1.5 mole of oxygen. We're still short of a 0.5 mole. But from here, you can see that it actually provides most of the hydrogen needed in an combustion power plant. So the downstream application, you can actually use it to produce the synthetic fuel, like for example, kerosene. So the entire system will expect to be having a very high efficiency. My last project is on the integration of an ammonia cracker into a solid oxide fuel cell system. So this is the illustration showing a cracker, ammonia, a storage tank, a cracker, and a solid oxide fuel cell stack. And you can see that the blue color, the light blue color is actually the ammonia. The green is the cracks, ammonia crack into the hydrogen and nitrogen. And lastly, the deep blue, dark blue color is the water and the nitrogen. So when ammonia is fed to this heat exchanger and then pass to another heat exchanger, we're expecting that the temperature is high enough for the cracker, knowing that the solid oxide fuel cell can operate from 500 to 900 degree. And if you select, ideally to select an intermediate temperatures solid oxide fuel cell rather than opt for the 900 degrees operating temperature solid oxide fuel cell. For the reason of the higher the temperature, the higher the NOx formation. So at 650 degrees C, we would expect insignificant kind of a NOx form. If you look at in the combustion engine, typically the temperatures is 200 Celsius or more than 200 Kelvin. So with a lower temperature of 650, the impact of NOx formation is very low. So feeding the so-called crack gases to the solid oxide fuel cell, and we would have because it is hard to have 100% of the fuel utilization. Normally we will operate at the 90% of the fuel utilization. The 10% of the hydrogens and the air can be burned off to produce the heat, so that this provide some of the heat to preheat the natural gas, right? So here is another interesting thing is that if you look at the catalyst, if you are able to develop an advanced catalyst using ions supported on ceriums and zirconium oxide, and you can see with a ratio of 31 and 5, we can achieve a 100% kind of a conversion at a 427 degree. So the burner here have a temperature, much higher than this temperature. So it is more than sufficient to heat up the so-called the gas, or ammonia to the desired temperature for cracking. So this cracker is actually served as a so-called waste energy recovery, because when you feed in the ammonia with a certain heating values, after cracking, it becomes the heating values is increased by 14.2%. This is because of the waste heat, which also contributed to the heating values in the ultimate hydrogen. So that is a very interesting concept. Without any movable part in the system, the likelihood for the ammonia cracking will be a very minimum. So I think that I like to end my presentation here. Thank you.
Thank you, Prof. Chen, for sharing with us the exciting activities that are going on at NTU. Just keeping an eye on the time. So let's move on to our final speaker. And of course, would like to encourage everyone to continue to ask questions and post them into the chat box. Okay, so our final speaker is Dr. Adam Usadi, Energy Center Advisor from ExxonMobil. Adam is progressing a portfolio of R&D focused on low emissions energy and products at the Singapore Energy Centre, jointly founded by NTU and NUS. Adam's presentation today will be on energy research from an industry lens, and it's entitled Energy Research to Provide Solutions for the Dual Challenge. Handing the time over to you, Adam.
Thank you, Connie. Connie, can you confirm you can see my slide?
Yes, I can see it. Thank you.
Thanks very much. First of all, thank you for inviting me to speak, and I'm honored to be on the same virtual stage as Dr. Chen and Dr. Chen. It's I see the presentation just before me, and we're pretty closely aligned on the way we think about things, and so hopefully they'll feel the same way about what I'm talking about. I'm based in Singapore. I'm from ExxonMobil R&D, and so my perspective is from our R&D organization. And I'd like to just paint a picture of some of the R&D that we're progressing at the Singapore Energy Center. And I'd like to start with just one way we are thinking about current energy demand. So between now and 2040, the population of the world is probably going to go up to well over 9 billion people from today, which is just over 7 billion. The GDP is expected to double. And that's really important because that drives energy demand. And the title of my talk is The Dual Challenge. The dual challenge is supplying the energy and chemicals and products that the world demands while mitigating environmental concerns, including climate change. And that's hard. We know with the recent pandemic what it's like. If we want to shut down the economy, well, we can mitigate CO2. But if you bring the economy back, you need to solve both at the same time. So that's sort of a key issue. Now, what's shown here are the results of the 2018 Intergovernmental Panel on Climate Change Special Report on Global Warming. It identified 74 scenarios. So this is an output of modeling studies or energy systems analysis, which were pathways to meet energy demand by 2040, limiting global warming peak to 2 degrees C throughout the entire 21st century. So what this is a snapshot in time, and these are the outputs of different scenarios, 74 different scenarios known as the lower 2C scenarios. And the colors are the supply, and you're going to see hydrocarbons, oil and gas, as well as renewables and so on. And what you can see, and it's just sorted by a seriatim from lowest to highest, that based on assumptions and things like that in the model, you get kind of different results. It's a bit all over the place, but not wildly different, to be honest, and not too far off. And then on the right side, the left of the right columns is the average of the results of these scenarios. And the right one is just for comparison. That's the IEA SDS 2040 scenario, a sustainable development scenario. So what does this mean? So to put this in perspective, let's compare the 2019 energy demand mix versus the IPCC 2040 average mix. The color scheme, unfortunately, is different in this plot. I'm sorry for that, but the left figure here is the 2019 energy demand mix, and the right one is the average from the 2040. And what you're going to see is a few things that are kind of interesting. One is that energy consumption in 2040 is less than 2019. In other words, to keep to the 2 degrees C scenario, we need to actually be consuming as a world less energy than we are today, with a much bigger population and a much larger GDP. So this really strongly implies a need for significant energy efficiency improvement. In other words, we need to use energy to do more with consuming less of it. There's obviously a very significant growth in low carbon energy, renewables, and so on. Interestingly, it shows that oil and gas still constitute about 48% of the total energy demand. So then how are we doing on our way to this 2040 sort of view? Well, if you compare how we did from 2010 to 2019 and just sort of the rates of growth of everything and so on, you can see that historical growth rates for wind, solar, bioenergy, nuclear is actually much lower than what's needed. That's including extremely rapid growth in places like China. The energy demand for oil and natural gas and coal is higher. The growth is higher than what these IPCC scenarios suggest would be needed. And the energy efficiency improvements have not been fast enough. So that's sort of the state. And so then the question is, well, how do you focus on this really large scale CO2 mitigation? Now, this plot is from ExxonMobil's Energy Outlook from 2019. It's pre-pandemic, so it's probably going to be slightly changed from 2000 to 2020. It's historical numbers, and then post that it's a projection. And it will probably be modified based on the pandemic, although not as much as you might think. I've been reading lately that China's energy consumption and emissions are back up to pre-pandemic levels. And as the world recovers, it probably will look slightly different, but the basic thrust is that the emissions are quite large by the 4 sectors. So it's electricity generation from all sources, natural gas, coal, and so on. Industrial sector, which includes our industry, petrochemical, manufacturing, agriculture, and then transportation, all sources, trains, planes, automobiles, and ships, very importantly from Singapore's perspective, and then the residential commercial. And so this says, okay, fine, this gives us sort of a way to think through what is the R&D we want to focus on. And it's basically to focus on wedge scale or really gigaton scale energy, CO2 mitigation. So starting from the electricity generation, this is ExxonMobil's perspective. We're focused a lot on natural gas, which is 95% plus more of Singapore's own electricity generation, with CCUS and the renewables and energy storage, grid energy storage. Then on the transportation side, on the industrial side, it's reducing the emissions and the energy intensity and the emissions intensity associated with manufacturing. Once again, this is ExxonMobil's perspective. What do we do in the refinery and the chemical plants on Jurong Island and nearby? We convert chemicals and we move fluids and we cool and heat things. And so it's new kinds of catalysts and new kinds of processes is going to be a big important part of energy efficiencies improvements. And then of course, CCUS and hydrogen, where you'd have some sort of fuel replacement for some of those activities. And then on the transport side, hydrocarbon is still going to be a major part through 2040. But of course, batteries for transport, hydrogen and biofuels. And then on the residential commercial, it's new kinds of materials to reduce the emissions intensity, the energy intensity of construction and operations. So just focusing a bit more on CCUS, because that's a big topic today, and it is a big topic of what we're doing in Singapore. For some background context, ExxonMobil has a working interest in more than 1/5 of the world's capacity, capturing about 9 million tons of CO2 a year. That's a lot, but it's not nearly enough. I will definitely concede that. And actually, over the past 30 years, ExxonMobil has captured more CO2 than any other company, accounting for about 40% of cumulative CO2 captured. Earlier this year, ExxonMobil announced a new low carbon solutions business. Initially, they plan to advance a number of carbon capture and storage opportunities around the world, including, they explicitly mentioned, Singapore, Southeast Asia target as well. They plan to invest about $3 billion through 2025 on commercial CCS projects, not R&D. So the R&D I'm talking about now is not part of that, but it's rather feeding and supporting the LCS, the low carbon solutions team, which is important because we're focused on the next generation of CCUS technologies. And in fact, we're focused on technologies with lower CapEx, lower physical footprint, which is really significant for Singapore, that require lower energy for operations. And I show you the buckets of how we're thinking about it. The cost and the technologies very much depend on the concentrations of the CO2, as you might imagine. I kind of had 3 large buckets. Of course, as you get into the details, you can subdivide it a lot more. So on the industrial side, you can have relatively high concentration, 60%, but even in the industry side, burners and so on are down to 8%, which is low. On power generation, 4% is the CO2 concentration from a very efficient next generation natural gas combined cycle power plant, but 14% is up to coal. Indonesia nearby is a big consumer of coal for power generation. And then of course the extreme other end is direct air, where it's much less than 1%. So our R&D, just as sort of an R&D way of thinking through things, we're focused on new kinds of materials. So for liquid and solid based carbon capture technologies, as well as carbonate fuel cells, which is something we've talked about publicly in the past. Here, the research is focused on materials with high working capacity, fast transport kinetics, and low regeneration energy. Then you take those materials and you need to put them into some sort of contactor that can interact with the flue stream, so you can actually access and touch a lot of the CO2. So the research is on modular and easily scalable with a small physical footprint and therefore a high volumetric capacity. And then once you have those, you need to come up with an optimal process or a process that's amenable to retrofit and transient operations. I mean, we're not even talking about that here, but natural gas peaker plants will probably become increasingly important as renewables grow on various grids. And so, sort of transient operation CCS is going to become increasingly important. And it must have low utility requirements, low toxicity, and all those kinds of things. And then finally, of course, there's the disposition. What do you do with the CO2 after you've captured it? A big thrust, and I have to say that ExxonMobil's primary thrust is mostly on the sequestration in the underground, either in depleted oil and gas fields or saline formations. And that's primarily because that's what you can do at scale today and probably for the near future. But of course, utilization, as very nicely described by Prof. Chen, is an interesting topic from a research point of view. That's a little bit earlier on the technical readiness level, but you can certainly convert the CO2 into other products as well. So I'd like to end with talking a bit about some projects that are being progressed at the Singapore Energy Center. And these projects on the left are known in the Singapore Energy Center lingo as core projects, meaning that these are not collaborative with ExxonMobil. These are funded by the Energy Center like a consortia. They were selected by a committee. These are 5 of the 6 projects. And I'll just quickly mention them. They're on new materials, metal organic frameworks for, as I mentioned, for where the applications would be. Methane cracking, I will not dare to touch that because that is Prof. Chan's project, and it's really it's a piece of course, of what he's been doing over the years. CO2 capture and utilization using the fly bottom ash and brine from the Singapore's material waste facilities, as well as the desalination plants. Very interesting, combining 3 grand challenges at once. It's kind of it's a tough nut to crack, but it's very interesting. Membranes for CO2 separations. Membranes really require a high partial pressure of CO2 to be a driving force to do the separation. So membranes for CO2 separations probably more useful for, not for power generation where it's at atmospheric pressure, but for other things, potentially, steam methane reforming or other processes that have high pressures. And then finally, photoelectrolysis for renewable hydrogen production. Similar to the challenges there were actually identified very nicely by Prof. Chen. Most green hydrogen today, all green hydrogen today for that matter, is really generated from water, not salt water. And so there are a host of issues. In addition to those mentioned by Prof. Chen, seawater is filled with microbes. So there's microbial corrosion, all those kinds of things. So it's really an interesting project. Now I'll highlight just very briefly a few of the many projects that we're progressing collaboratively. ExxonMobil working closely with research scientists at NUS and NTU today. And A-Star recently joined the Singapore Energy Center, which we're very excited about. And so we look forward to working with A-Star as well. Once again, we've got projects on new kinds of materials for carbon capture. In this case, it's COFs, covalent organic framework, COF, very similar to MOFs. And by the way, all the projects, both on the left and on the right, are targeted to publications. Everything is going to be out there. And in fact, there are a number of publications out of both the left and the right. The ones on the left, you can find reference on the website for the Singapore Energy Center. We're also quite keen on, digging to the details of where Singapore could put its sequestration, its CO2 in the region, looking regionally. We know there's a mature oil and gas industry and therefore depleted oil and gas fields in Malaysia and Indonesia, Brunei, Vietnam, and so on. And so working with researchers at NUS to sort of quantify that and come up with approximate estimates for costs and so on. We're actually finishing up that work right now. Additionally, there are other ways to sequester CO2 with a professor at NUS looking at hydrates as a different form of CO2 sequestration. It's a little bit earlier on the technical readiness though. Then the third one is more of an energy system study sort of touching on the hydrogen import from Australia example that Prof. Chen gave. Here it's a supply chain optimization problem, really. And it's basically, should Singapore import its CO2 as in the form of ammonia from Australia? Should it import it as a gaseous hydrogen from blue hydrogen from Malaysia, where Malaysia could do steam methane reforming maybe a little bit more easily since they have the sequestration options? Or should Singapore do its own methane cracking and therefore handle the CO2 that way? So it's more of an energy studies. And then finally is one sort of different example, leveraging the incredible biodiversity in Southeast Asia. You've probably heard that research scientists are constantly using bioprospecting, looking to nature to inspire new designs and new kinds of enzymes, inspire catalysts, and so on. And here you can find locally, in fact, I went with the postdocs to Pulau Ubin, and you could find a velvet worm. It's really hard to find, actually. You have to run around through this, the leaves and so on. But they shoot out a polymer like Spider-Man, and they catch their prey, and the polymer hardens really quickly. So our chemical company looks at that and goes, oh my God, you could build a building with a fire hose. I mean, that's a dream. But the research is on understanding what's causing the mechanical performance of that polymer. What are the proteins? Where are the proteins? What are the genomics that are sort of leading to the synthesis of those proteins in this velvet worm and so on? So we're very excited about this portfolio of research, really touching on decarbonization from many different threads. So thank you very much.
Thank you, Adam. Thank you so much for sharing with us your industry perspective as well as the work that's going on at the Singapore Energy Centre. And I'd just like to thank our three speakers once again for your presentations and for sharing with us on the current landscape of work being done on decarbonisation. I'm just going to keep an eye on the time. We have a few minutes left, but maybe we'll ask the panelists to help us with one of the questions that came up. So one of these questions from the audience are, by 2030, which new technology, for example, carbon capture, CO2 to chemicals, hydrogen economy, waste to chemicals, plastics to chemicals, would you consider as a game changer, such that it plays more of a dominant role than simply just increasing energy efficiency? So that's for any of the panelists or all three panelists, if they would like to chime in on this.
I can take a first shot. I would say everything listed by Tej, whose office is right next to mine at NTU, is important. And we don't know what the winners are going to be, to be honest. From the way the question is formulated, it wasn't clear if he's saying which of these energy efficiency things are going to be dominant, or because I would put energy efficiency in kind of a different category. A lot of these are like carbon recycling and so on, or other things like carbon capture and sequestration. I would not necessarily pitch that as an energy efficiency. That's a CO2 mitigation technology. Energy efficiency is probably trying to do more, use your energy more efficiently, achieve what you need with better catalysts and so on. But we don't know what the winners are going to be. So we need to sort of work on all of these things. And entities like the universities and A-STAR can sort of help grow these all at once. And you don't have to pick and choose winners at the beginning, because you don't really know which ones are going to be the winners, but you can sort of steward them through the development cycle and then maybe decide, okay, this one's looking a bit more promising.
Well, I had to
Thank you, Adam.
the remark here that
sure.
When it comes to the energy's transition and the futures, deep decarbonization of the economy, the energy efficiency alone is not enough. If you listen to Minister Chan Chun Sing's share the Singapore's energy storage, the 4 switches. The 4 switches is actually corresponding to the first, continued use of the natural gas, and the emphasis is on the energy efficiency. The second one is the adoption of the solar energy, solar PV, to generate the power as much as we can. And we know that the 2 gigawatt is the so-called the target by 2030. The third one is energy management, right? It's like, whether we can connect the ASEAN grid so as to tap the energy from our neighboring country. The last switch is actually alternative energy, alternative fuel, including the CCUS. So you look at it, the government actually has a plan very nicely that not just a focus on a single energy efficiency alone, but covers the very broad spectrums to ensure that we can reach the goal with these 4 switches. Thank you.
Does Leeway have anything, Prof. Chen, have anything to add onto this? Okay. Okay, so it's 2 minutes past 5. So thank you once again to our panel members and our speakers for today. Prof. Chen from ISIS, Prof. Chan from NTU, and Dr. Adam from Exxon for sharing your valuable insights on the current state of decarbonisation technologies. Indeed, there are many challenges that lie ahead, and the complexity of such a problem requires a concerted approach among our research performers, our HLs, government agencies, and industries to be successful. So from the lively discussion and from the presentations, I can see that this is really just the beginning of how we can bring this ecosystem together. And I hope that we can continue this dialogue offline with our fellow collaborators and contacts that are working in this area. I hope the technical workshop has been informative for you. And I am looking forward to seeing how this area evolves as low carbon technologies become more mature. And with that, thank you for joining me here today. I wish you a good evening, and I will hand the time back to our MC for the main